Good morning, everyone. Today we will continue our topic, RL circuits. We will look at the inductor response and several circuits. So let's start with this circuit here where we have two switches, switch S1 and S2. When the switch S1 was open and S2 was at position A, we closed S1 at t equal 0. So what's going to happen to the inductor? The inductor now is going to see an increase in the current. And as we have seen earlier, the increase of the current is going to result into a potential difference, that is the induced electromotive force, due to this current that opposes the increase in the current. So if I write the KVL equation for the potential differences across now the battery here, the resistor, and the inductor. This is the Kirchhoff's voltage law for this loop. In this case, epsilon minus IR minus L di over t dt equals to 0. We're not going to go through the derivation of the current function for the case of the inductor in a circuit where the current is increasing. So this is the current expression for an inductor that is seeing an increasing current. In this case, the current here will increase exponentially till it reaches the maximum value, which is here epsilon divided by R. So this is the final value here. This is IT and this is T. So this is the current response for an inductor that is seeing an increasing in the current. And this is the expression for the current when the current is being decreasing or the inductor is discharging the energy stored in it. And this happens when I switch S2 after a long time to B. So in this case, when I switch S2 to B, now the inductor already accumulated energy in it, then this inductor now will start to discharge this energy. In this case, the inductor will be replaced with a current source such that the current at that moment equals to the current that was going through the inductor when the switch was at A for a long time. What we need to know here that this is the function for the inductor when the inductor is discharging the energy, and this is the function for the current also for the inductor when the current is increasing, and at that moment the inductor is storing the energy. And this is the response for the increasing current in an inductor, where the maximum value here is epsilon divided by R, and at tau, the tau happens before I reach point. This is the distance here is 0.60, 0.32 or 32.8% from the final destination, or I can say that this one is 0.632 epsilon over R. Now consider the circuit with S1 being closed and S2 at position A. Switch S2 is now thrown to position B. At the instant it is moved to position B, what is the voltage across R? So before we calculate what is the voltage across R when the S2 was thrown to position B, we need to calculate the current in this inductor when this switch was at A and S1 was closed. So in this case, we are gonna go and draw the circuit here when the switch was at A, because the information we're going to get from the circuit when the switch was at A before going to B is going to help me in calculating the voltage across R. So let's start first with the first circuit. So I have here, this is the R plus minus VR. So the switch was at A, switch S1 was already closed and was closed for a long time. So now, how are we going to deal with this inductor when this switch was closed for long time, or this switch was at A, which means it was at A for a long time. Now, in this case, the inductor is going to be a piece of wire. Why? Because once the switch was closed for a long time, my voltage across the inductor, which is, as we have seen earlier, minus L di over dt. The current is not changing with time anymore. That's why the di over dt is zero, which means that the VL is zero, and this is equivalent to a wire. So the inductor, when the current is constant, the current is not changing with time, the inductor can be replaced by a piece of wire. So in this case, I can calculate now the current. I can calculate this current that goes in this inductor, and here I would be epsilon divided by R. So this is the current that goes in the inductor. Now, when the switch S2 was moved to position B, at the instant it was moved, the inductor now will be replaced by a current source. So at the beginning, we have seen that the current is going in this direction, I. Now, when I move the switch from A to B, I will have now only the resistor R, and now the inductor that will be replaced by a current source. This current source will be generating a fixed current. Now this current at right after the switch is closed is moved to B. This current now would be equal to the current I that we have calculated earlier. So I equals to epsilon over R. And this is R. So in this case, right at this moment, what's going to happen? So here I have plus, minus, VR. So this is the VR. Right at this moment, the voltage VR will be R times the current. However, the current is epsilon over R, which means that the voltage is going to be epsilon. So this is the voltage across the resistor right after the switch was moved to B. So the answer is epsilon B. Now let's move to the next question. Here we have consider the circuit below. Switch S is closed at t equal 0. What is the voltage across the inductor L just after the switch is closed? Now remember, the current that was going into this inductor when the switch was open was zero. There are no source of energy, so the current was zero through the inductor when the switch was open. Now, right at the moment when I close the switch, the current is continuous through the inductor, so the current is not going to change. So the current right after I close the switch will still zero. And that's why we say that the inductor, when it has no current going through, when I put it into the circuit, at that moment, it will act as an open circuit. So I can now redraw the circuit here and treat this inductor as if it is an open circuit. So the battery here, so I have 2 ohm, 1 ohm, 6 volt, which means that the voltage here across the inductor indeed is the same as the voltage across the 2 ohm. So how do I calculate this? First of all, I need to calculate the current. So I know that the current equals to 6 divided by those two resistors are in series, 1 plus 2. So I is 2 ampere. Then VL is the same as the voltage across the 2 ohm. Then VL is the 2 ampere times the 2 ohms, and VL is 4 volts. So the answer is C. Now let's move on to the next question. Here we have consider the circuit below. Switch S is closed at t equal 0. What is the current through the inductor L long time after the switch is closed? So the word long time means that I don't have a time dependent value anymore. Long time means that di over dt is 0 now. Why? Because the current now is going to be a constant, which means that the di divided by dt equals to 0. So in this case, when I hear the word long time, I replace the inductor with a piece of wire. The inductor is going to act now as a wire. So with a zero resistance, which means now when the switch was closed and long time, my circuit now is going to look like this. This is the inductor, a piece of wire. Why? Because di now divided by di over dt is 0. So this one now is going to act as a piece of wire, which means that this wire now has shortened out this 2 ohm. So now all the current is going to go take this path. So this is now my current. If I want to calculate the current in the inductor, it would be the same current in this circuit, which is 6 divided by 1, and the current is 6 ampere, and the answer is D. Now let's move on to the next question. Here we have this question. Two circuits, identical batteries are connected to two identical inductors as shown here. So the only difference, the switches are closed for a very long time. So the switches were closed for a very long time. At t equals 0, both the switches are open. So at t equals 0, so they were closed for a long time. And now at t equals 0, they were open. So the only difference here is the resistor here is 2, the resistor here is 1 ohm. We need to calculate or find out which resistor dissipates more total energy after the switch are opened. Okay, so here we need to first draw the circuit when the switches were closed for a long time in order to understand the, the energy stored in those two circuits. So here we have the first circuit as 3, 2, 6 volt. So when the switch was closed for a long time, remember this means the inductor is replaced by a piece of wire. So this is for B, this is for A. Okay, so in this case, this resistor and this resistor will be shorted out, and the current going into the inductor for, let me call this one IA and IB, those currents are going to be the same. So I have IA as 6 divided by 3, 2 amperes, and I also have IB 6 divided by 3 is 2 ampere, which means that the energy stored in those two inductors, as we'll see later on, would be the same. Why? Because the energy equals to half L I squared, as we will see later on, but let's use this one now here for the time being. So we have identical inductors, and we have now the same current, which means that the energy stored in those two inductors would be the same. So now this is what we have found. When now the switches are open, what's going to happen is the following. I have now this inductor that had the current going through this way will be now replaced with a current source, and the value of the current is 2 ampere. This is only at the moment right after the switch was open. So this is right after, and this is for both of them. Are open. So this one is 2 ohm for circuit B. For circuit A, the only difference. So this is also 2 ohm, 2 ampere, and this is 1 ohm for circuit A. So the only difference now that the values of the resistors, and again, this is right after the switch is open here and there, then the value is going to change based, if you recall, on the function that we have seen, which is epsilon over R E minus T over tau. So this is the maximum, which is the 2 ampere here in my case. right? This is the 2 ampere here in my case. And then the current is going to decay exponentially. But now the question is asking the following: which resistor is going to dissipate more energy, more total energy? Now, at the end, both resistors are going to dissipate the same amount of energy, the same total energy. Why? Because the energy stored in both inductors are the same, and both of those energy are going to dissipate into those two resistors. However, the rate of dissipation is going to be different, but the total dissipated energy is going to be the same. However, the rate of the dissipated energy would be different. But the question here is asking about which resistor dissipates more energy, and the answer is both resistors dissipate the same amount of energy because both inductors are storing the same energy. Okay, so in this question we have switch is left in position A for long time. Again, we know now what does this long time mean for long time interval, and is then quickly thrown to position B. Rank the magnitude of the voltages across the four circuit elements right after the switch is thrown to position B from largest to the smallest. So now the question here is asking us to rank the voltages in those components. So now let's draw the circuit when the switch was at position A. Because it was at position A for a long time, we want to see what information can we get out of the circuit. So remember when the switch was at position A, inductor is a wire. So this is very important to understand. Why? Because when it's for a long time, my voltage source here is a DC. DC means di over dt equals to 0. So only when I switch either open or closed, at that moment I will be having a time varying current. But once I reach to the long time after the switching, then my current now is going to be a DC current, then di over dt would be 0. So in this case, I will draw the circuit when it was at position A, and in this case the inductor will be replaced by a piece of wire. So I have here a 12 ohm resistor. At position A, I only have this voltage source, which is 12 volt, and I have this resistor and the inductor as a piece of wire. So what information can I get out of this circuit? The information is the current. So I can now say the current is 12 divided by 12. So the current is 1 ampere. Now when the switch moves to position B, right? My circuit now is going to be the following. So what do I replace this inductor now right after the switching? Again, the inductor will be replaced with a current that equals to 1 ampere. So here we have a current source. This is the inductor. We have now this resistor, 12 ohm. We have a second resistor that is 1200 ohm. So remember this current right at the moment. This is only right after S goes to position B. So now this one becomes 1 ampere. Now we need to calculate the voltages because I need the voltages. Now the voltage here for the 1200 ohm becomes 1200 volts. The voltage across the 12 ohm, again, it is the current times the resistance. So V12 as 12 volts. I know the epsilon as 12 volts, constant, it's not going to change. Now I need to calculate the voltage across the inductor. How do I do this? I can do this by knowing, for example, the current as I naught. Here now the current is decaying e to the power minus t over tau. So what is tau? Tau is L over R, which is 1200 plus 12, and L is 2 Henry divided by 12, 12. So tau is 1.65 10 to the power minus 3 seconds. Then I have here IT equals to 1 E minus T over 1.65 10 to the power minus 3. So now in order to calculate the voltage across the inductor, I can use VL equals to minus L di over dt. So VL is minus L. What is di over dt? Di over dt is minus 1 over 1.65 10 to the power minus 3 e minus t over tau. So VL equals to minus 2 times minus 1 over 1.65 10 to the power minus 3 e minus t over tau. So I'm interested to know this because this is going to be the maximum voltage right after the switch. So VL is 2 10 to the power 3 divided by 1.65 e to the power minus t over tau. And now V naught equals to 12 volts, which is the voltage across the inductor right at the moment where the switch was moved to B. And also, if you think about it, and if you take a KVL right at this moment, what do I have? I have here, I have the voltage across the inductor equals to the voltage across the 12 ohm plus the voltage across the 1200 ohm. I know the voltage across the 12 as a 12 volt, and the voltage across the 1200 is 1200, then the voltage across the inductor will be the summation, which is 12, 12, and this is what we have found here. So I can say that the VL across the inductor was the greatest. Then comes the V1200. Then comes the epsilon that also equals to V12 ohm. So the correct answer to this is is A. Now the energy stored in an inductor, we have seen earlier that the inductance is the flux divided by the current. And we also have seen that the potential difference across the inductor is minus LdI over dt. Now the power would be this potential difference times the current, which is Li di over dt. So this is the power. Now if you want to calculate the energy, then we need to integrate the power over time. Now integrating the power over time basically means that I can now here use two different separation of variables and integrate the power over time and integrate the current from 0 to I. Doing this will basically give me now the energy for the inductor, which is half Li squared. We've seen it in a few slides before. So this is the energy stored in the inductor that equals to half Li squared.